Hello, everybody. Welcome to today's current seminar. Today we have two speakers, two talks. Our first speaker is Yixiang Deng. She will be giving a talk on exploring the frontiers of computational medicine. Yixiang Deng is currently a postdoctoral fellow at Ragon Institute of Mass General, MIT and Harvard, with a joint appointment at the MIT Department of Biological Engineering. Her research focuses on integrating knowledge-driven and data-driven computational models to probe the mechanisms of diseases and the effectiveness of therapeutics. Before joining the Ragon Institute, she completed her PhD in the School of Engineering, advised by Professor George Karniadakis at Brown University in 2021. She received a bachelor's degree in engineering mechanics at Shanghai Jiao Tong University in 2015. With that, the floor is yours and you can start your presentation.
Thank you so much for the kind introduction. Today is my honor to present my work on exploring the frontiers of computational medicine, integrating machine learning and multi-scale modeling. So due to the inherent complexity of coupled nonlinear biology system, the development of computational model is essential to achieve a quantitative understanding of the structure and function of health and disease. Machine learning is applied in high-dimensional biological data to create models that describe association between molecules and networks. Multi-scale modeling links network to the cells, organs, and organ systems. By integrating multi-scale modeling and machine learning in classical and molecular epidemiology, the disease mechanism is better understood at all levels. These extend from individuals to the environment in which we live, provide us with opportunities to provide different disease states, predict healthcare risks, and establish innovative and effective health solutions. So in the following, I'm going to talk about my work on integrating machine learning and multi-scale modeling to explore the frontier of computational medicine. I'll first start with the multi-scale modeling. So I want to start with a very interesting phenomenon of thrombus formation, which is very dangerous and complicated. Thrombus is represented by aggregated platelets or red blood cells that form a plaque and with a mesh of cross-linking proteins. Thrombus formation can happen in many organs like brains, lungs, and hearts, and leading to very devastating disability or death. Some study has shown that red blood cell aggregations can promote thrombus formation, white blood cells adhesions can also promote thrombus formations. However, it remains unclear how these factors altogether contribute to the thrombus formation. So I'm interested in developing multi-scale modeling to study the thrombus formation. And the reason that I choose in silico model is that first, it can replicate in vivo and in vitro observations. Second, it can offer on-the-fly tuning of the model. And third, it can help connect dots and help us elucidate the mechanism of thrombus formation. And the way I'm using the in silico model is that I develop particle-based simulations satisfying physical and chemical constraints. I'm going to illustrate in the following different perspective of thrombus formation, starting with mechanics of excessive aggregation of red blood cells. So typically, our red blood cells can adhere to each other and forming these red blood cell aggregations in our body. However, it's simultaneous, it's a reversal process in healthy patients, whereas in patients with some disease, for example, diabetes, they can form these very long aggregates shown here in the like a capillary structure. And this actually increases the capillary blockage risk. So informed by this observation, we work with Dr. Ming Dao and his postdoc at Massachusetts Institute of Technology, who developed this capillary network. Doesn't work. Oh yeah. So you can see from the image that we have the red blood cells passing through like microfluid devices inspired by the capillary network. And follow this observation, we also design our in silico microfluid devices depicting the capillary network. Also, in the meanwhile, we noted that fibrinogen, which is an abundant molecule existing in the blood, can increase blood viscosity and promotes red blood cell aggregations. So the question that we are interested in exploring is that, can we simulate clinically meaningful red blood cell aggregations? And specifically, we want to develop patient-specific red blood cell aggregation models. So from clinical observations, we found that fibrinogen concentration are kind of proportionally creating different red blood cells of different adhesive properties. So we hypothesized that the adhesion strength is proportional to the fibrinogen concentration of the blood. And we construct the red blood cells by this triangular meshed structure. Each cells represent either adhesive particles or non-adhesive particle denoted by the red color. And we validate our in silico design using the in vitro experiments, in that we quantify the most basic red blood cell aggregation, meaning the doublets where there are two red blood cells adhere to each other, and we observe whether they disaggregate or aggregate under the flow condition. And we found that our model construction matches very well to the in vitro observation. And we, by observing how many percentage of the doublets have been simulated, and they match very well, depicted by the bar length of the original color and shaded color. This design also inspired the blood simulation in hyperviscosity region, which also adopt our fibrinogen-dependent red blood cell aggregations in collaboration with Dr. Javadi and Safa at Northeastern University. So the next, I want to explore how the morphology of the blood vessels affect the thrombus formations. So again, in diabetic patients, some of them develop this diabetic retinopathy and has this phenomenon of a swollen vessels around in their retinal area, and this swollen vessel is called microaneurysm. Microaneurysm has the possibility of being having clot or rupture, and may cause a blindness for some patients. And cell transport is very contributive to either the clot rupture process. Therefore, in this project, we want to quantify how some important physical quantities will affect the cell transport in microaneurysms. For example, how is the flow rate of the blood affect the transport, and how is the morphology, meaning the size of the microaneurysm, affect the cell transport. And specifically, because we have this big like a bag structure, we define a morphology metric to be named BNR, defined by the body to neck ratio depicted here. So what we did is that by collaborating with Dr. Song from Joslin Diabetic Center, we acquired this as an oslo image, which is the most high quality image we can get from patients in vivo. And this actually gives us the morphology of the microaneurysm. However, because the limitation of the current technique, it's very difficult to get the cell dynamics in vivo. And by collaborating with Ming Dao from MIT, we also designed these in vitro experiments which capturize the microaneurysm, the morphology very well, yet the cell dynamics is a bit tricky to capturize. Inspired by this, we construct our pathologically meaningful in silico model. For example, here I'm showing you a specific BNR microaneurysms. And by conducting multi-scale modeling, we can extract the cell dynamics when passing through the microaneurysm, where the white line denotes the platelet trajectory and the red line denotes the red blood cell trajectory. And what's more interesting is that we can offer both qualitative and some quantitative effect of the important factor that we care about, depicted by this image of dependency of platelet entering the microaneurysm on the morphology and the different flow rate. So in the next, I also want to discuss how the multi-processes nature of the thrombus formation affected the blood clot. So we observed clinically that 91 patients died from SARS-CoV-19 had this microthrombosis, which is a multi-process phenomenon involving in both blood cell mechanics, coagulation cascade, and transport of coagulation factors and those cells, as well as the cell adhesive dynamics happening at the thrombogenetic site. So to simulate the microthrombus formation, especially the coagulation cascade, we use a 21 coupled ordinary differential equation depicting the dynamics, the chemical species of 23 chemical species like coagulation factors. And we parameterize our model inspired by clinical data from the patient sample acquired by working with Dr. Freiman at Mass General Hospital. And to solve the advection diffusion reaction equation, we adopt a transport dissipative particle dynamic methodology developed by Dr. Li. And we found very interesting pattern about the platelet aggregation. And specifically, we found that our simulation can model the similar phenomenon observed in the similar mouse study. I call it promotive than prohibit flow velocity dependent platelet aggregation, meaning that as the blood velocity increase, the growth of platelets increase, while it reach a threshold. For all the simulated cases, the growth rate actually decrease. And more interestingly is the critical flow velocity for this phenomenon to be happened increase with higher TF tissue factor 7A concentrations. So in summary, I have presented how multi-scale modeling can recapitalize the biological events, for example, red blood cell aggregations, blood cell transport, and chemical species transport. I also presented how the multi-scale modeling can offer on-the-fly tuning of the model with patient specificity and morphology of the vessels. And also taking all this all together, it can help us enhance understanding of thrombus formation and other cell-cell adhesion. And envision the broader impact of multi-scale modeling can be used to design drugs to, for example, decrease blood hyperaggregations or blood hypercoagulations. So next, I'm going to move to machine learning. And specifically, I'll first talk about how machine learning aid biomarker discovery and how it helps us do time series forecasting. So SARS-CoV-2 has been affected almost globally for every people, and it causes severe deaths. And after infection or vaccination, our body actually generate this molecule called antibody, which have the Y-shaped structure, where the top to Y structure is called Fab. And there is another structure, part of the structure called Fc. So currently, to measure the antibody responses, we use a neutralization assay, which quantify how the Fab region binds to the viruses and how it interact with the virus. So this actually shows the quality of antibody of binding. However, as I mentioned, there's another structure Fc, which actually is linking to the cellular function that antibody can be signaling to. And in fact, only considering binding is not enough. We need to consider both binding and function to hinting to the protection of vaccination and infection. So the question I'm interested in exploring is to how to evaluate antibody function when novel pathogens invade our body. To answer this question, I use a system serology platform where the serum of patients after either vaccination or infection are profiled using two different assays. The first assay is called antibody biophysical profiling, which quantify antigen-specific antibody, for example, IgG1, which is the most abundant antibody existing in our blood, and IgG2, IgG3, and IgG4. And there is also FCR binding, which quantify how the Fc region of antibody binding to different receptors of our cells. And then another part of the more interesting profiling technique is antibody-dependent functional assays, which in which we put the antibody together with the antibody-antigen complex and put into some cellular-based in vitro assays to trigger phagocytosis or like complement depositions. And these actually generate this kind of, I call it fat data, where each rows represent the system serology measurement of each patient and each column denoting a different assays. And to analyze this data, there is actually some challenges. One, as I mentioned, is a fat data, which in where we have very expensive clinical trial, meaning that we have a limited amount of patients being admitted in the study. And by fat, I mean the dimension of a measurement is much greater than the sample of a dimension of the samples or patients. And second, because we're interested in understanding how SARS-CoV-2 immunology is, yet it's a novel viruses, which means we have really limited understanding about it. So my goal to understand, to use machine learning approach is to distill the novel immunologies, and I hope my model will be generalizable to other similar cohort infected or vaccinated by SARS-CoV-2. And to develop machine learning model, I'm specifically interested in developing linear model because first, it's the coefficients are meaningful, so give us interpretability. And also, second, it's a linear model, meaning it's a lower order machine learning model, which will have less chance of overfitting for small data scenarios. So here I'm showing you the specific pipeline of machine learning approach to distill novel immunology for systems serology platforms. Suppose we want to separate the feature, we want to find those features to distinguish group P1 and group P2, denoted by different color of the dots. So the first step we do is we do dimension reduction, which will be able to discrete the overfitting probabilities. And second, to visualize how the separation is, we project the latent space, project all these features into a 2D latent space to see how they separate in these visualizations. And third, we take out the coefficient of the features, and then for example, I show here the projection of each feature in the latent variable and color by different color. When it's green, it means the corresponding feature is higher in group P1, and when it's red, it means the corresponding feature is higher in group P2. And the sign of the loading is also meaningful, that if it's negative, meaning that the feature is driving the separation to the left to the left in the 2D latent space. While if it's positive, meaning the feature is actually driving the separation in to the positive panel of the latent space. So here I'm giving an example of how machine learning can aid us understanding of the hybrid immunity in SARS-CoV-2. Specifically, in this study, we have two groups of patients. One is called hybrid immunity, meaning that they got infection with SARS-CoV-2 before receiving vaccinations. And then another group of patients is called vaccination only, meaning they didn't have any chance to be infected before the vaccination. And specifically, we are very interested in evaluating how different vaccine platforms induce different immunological signatures. And this is a joint work with postdoc Kaplonik at Ragon Institute, as well as Doc Goldblatt from UCL. So by employing the approach that I mentioned, we found that example of the machine learning I'm interested in I use is called lithographic, which separates the vaccination only group and hybrid immunity group very well, depicted by a good separation of these circles in both mRNA vaccine cohort and DNA vaccine cohort. And by looking at the latent loading plot, we found that interesting immunology is that the hybrid immunity actually triggers a better response in terms of S2 in both of the platforms, hinting that the next vaccine discovery maybe should favor S2, which is a conserved part of the spike protein, and maybe can be used to elicit a broader protection or immunity. So using the machine learning and system serology platform, I have also trying to understand how the vaccine route in influenza affected immune responses, as well as some protein vaccination responses against SARS-CoV-2 in non-human primate. This actually is a collaboration with Sanofi and really help them guide their vaccine design. Also, more recently, we also did the same analysis to mRNA vaccination against SARS-CoV-2 in kids under in a small age, and we receive very good feedback from either globally or in the online platform. And this was a joint work with the Mass General Hospital. So the next, I want to also explore how machine learning can help us perform patient-specific glucose prediction in diabetes. So why glucose prediction is important for diabetes? Note that the diabetic patients suffer from strong variability in their glucose levels, in that lower glucose will probably lead to coma, and high glucose may cause some cardiovascular disease. And so accurate glucose prediction can actually help a patient perform really good decision-making in either taking more food when they suffer from a lower glucose, or either taking some glucose-lowering drug when they have higher glucose. And the real-world diabetic glucose trajectory is shown here. Each line denotes the different patients, and we found that some of patients really suffer from the lower dangerous low glucose. And hope you understand that from this picture, we understand the glucose prediction is difficult because the glucose trajectory is very nonlinear, and also the requirement of timely prediction as well as the patient specificity also gave us more challenge of small data. So we try to understand this, we try to provide accurate glucose prediction using a data-driven glucose measure, meaning formulated by this data-driven approach, meaning that we want to use the correlation between the time series of glucose to taking the past glucose as an input to our model, and the model will then output how the future glucose is within probably 30 minutes or 1 hour. And this is a joint work with Dr. Metzoris at Harvard Medical School. So as I mentioned, there is challenge of nonlinear and small data. So to address the nonlinear challenge, we are interested in exploring a plurality of different time series prediction neural network model. For example, recurrent neural network, which is very good at capturing sequential correlations, and a convolutional neural network, which is very good at extraction spatial imaging correlations, and an interesting model transformer based on attention mechanism, which is a backbone of nowadays very popular ChatGPT. So how can we tackle the small data challenge? My approach is using transfer learning, which is actually also a very important technique in designing a currently popular foundation model. So what I did is that I train our model in a big data set, meaning, for example, we have 40 patients. I train the data set. I train our model in the 39 patients glucose trajectory, and then fine-tune the model on a target, the specific patient. And this strategy is also called a leave one out strategy. So now we tackle the small data with transfer learning. How is our result? So we actually achieve state-of-the-art performance in glucose prediction on an open data set. On the left, I'm showing the glucose prediction in a regression manner, meaning that we are interested in predicting exactly a level of the glucose. We can see that both our model and Bevan's model can outperform other model in different metrics. Different metrics, for example, mean absolute error and root mean square error in both 30 minutes in the future and 1 hour in the future. And when zoom in comparison to the classification, where we are interested in detecting hypoglycemia, which is a very low glucose level leading to coma situation, we found that our model actually achieved 10% more accuracy in detecting this low blood glucose level compared to Bevan's work. So in summary, I've presented you that linear model can help distill novel immunological knowledge from high throughput data set, even in a small data scenario like clinical trials, and guide vaccine designs. I also showed that combined with transfer learning, specialized deep learning model based on neural network can provide accurate prediction in time series forecasting like glucose predictions. So I'm envision the broader impact of my work is that I can provide data-driven models which can help interpret other omics data like single-cell RNA-seq, which is popularly used right now, and other signals like EEG, monitoring the functioning of a brain, and also ECG, monitoring how heart is working. So in the next, I'm going to share with you how machine learning model can aid the decision making. Specifically, the decision making I'm interested in exploring is glucose control in type 1 diabetic patients. So according to American Diabetic Association, there is many 8 million cases of type 1 diabetes globally, and 2 million Americans are being diagnosed with type 1 diabetes. And more devastating is that there are many kids being affected by type 1 diabetics, either through genetic traits or by some infections. And the symptom of type 1 diabetic is that they don't have a functioning pancreas to secrete insulin in account for glucose increase due to food intake. And in their daily life, because they're young, they take food which increase their blood glucose, and they exercise a lot to decrease their blood glucose. And currently, the popular treatment for type 1 diabetic patients is developing this so-called artificial pancreas. So the first step of the artificial pancreas is automatically monitor the glucose levels. And second is to calculate appropriate amount of insulin. And third is using some method to deliver it. There are many wearable techniques helping us achieving the goal for artificial pancreas for type 1 diabetic patients. For one, we have glucose monitoring, also shorted as CGM, to automatically monitor glucose levels. And for the third step, we have insulin pump, which can automatically deliver it. However, the second one is still very challenging, and specifically for type 1 diabetic patients who are young, we are wondering how can we optimize insulin dosage considering both food intake and their exercise levels. I've separating this goal in two steps. First is we want to construct an environment to evaluate the algorithm. And the second step is we want to develop algorithms to prescribe insulin given past glucose in a period using the wearable data collected. So let's start it with the first one. How can we reconstruct glucose insulin dynamics using only CGM? So current efforts can be separated into two parts. One part can be separated into different parts. For example, some people use data-driven models like autoregressive models and recurrent neural networks to achieve the goal. However, since it's data-driven, it's remain very limited interpretability, and because it relies on data-driven, it actually cannot capitalize the progression of disease. And more importantly, we need to constantly retrain the model to update with patients' most recent states. Another efforts will be a knowledge-driven model where we have different compartments of where clinicians working with mathematicians to develop this compartment model where each compartment are represented by different tissue and organ, and each lines will be representing how the interaction between organs and tissues are. Some interesting knowledge-driven models are Bergman's model, which is the most oldest model, and also Delamain's model, which actually was approved by FDA. However, only using knowledge-driven model, it's kind of very difficult to incorporate the wearable data, which we've seen before is very noisy. So my approach is to integrate both of them, and specifically, I'm focusing on also integrating the most important real data from the wearable devices. So the compartment model I'm interested in using is developed by Roy and Parker, which taking into account very many different external factors affecting glucose. For example, the insulin infused by the insulin pump, exercise, which is very commonly found for type 1 diabetic patients, as well as food intake. And the state of interest I'm interested in exploring is the plasma glucose, which shows how the glucose variability is, and also some functioning insulin and circulating insulin, showing how the insulin is being used in the body. And here I'm showing you the ordinary differential equation for the corresponding model. And with current technique, we notice that we can only observe the circulating glucose and marked by this purple color. And these hidden states, functioning insulin and circulating insulin, will be very helpful for us to understanding how the disease progression for a patient is. So our goal to utilizing this ordinary differential equation is that given glucose monitored by CGM over time, we want to obtain the hidden states denoted by the circulating insulin and functioning insulin, as well as the hidden parameters denoted by these different characters. And more importantly, we want to using patient-specific CGM data to obtain patient-specific states and parameters, to leading to the construction of patient-specific model for glucose insulin dynamics. So what's a patient-specific model and how can we get it? My understanding of patient-specific model is that every patient have their own parameters and it actually addresses the inter-patient differences. And the way I'm going to obtain the patient-specific model is that by solving an inverse problem. Specifically, I want to solve the inverse problem using a flexible form neural networks. To revisit the definition of a solve inverse problem, it means by inferring hidden parameters and hidden states governing the ordinary differential equation with partial observations. And in our case, we are interested in using the CGM glucose levels to get circulating insulin and functioning insulin. And the reason that I want to solve inverse problem using neural network is that first, it can be very useful in approximating the complex nonlinear pattern observed from the wearable data. And second, because there is a good feature of auto differentiation, which is very helpful in solving differential equations. And specifically, the neural network architecture is shown here, which is also called systems biology informed neural network to train a neural network which map from time to different states of interest. And we specifically designed the loss function to match the wearable data collected from the CGM and also the equation imposed by the compartment model, as well as some auxiliary loss to account for the initial value. So here I'm showing you an example of how solving this inverse problem enable us to getting the hidden states of circulating insulin and functioning insulin. As we can see that all these three lines depicting the forward will be representing how the hidden parameter is inferred, and the predicted will depicting how the neural network inferred is trained. It matches very well in the observed states. So now that we have a functioning model, the second step is that we want to develop algorithms to prescribe insulins given past glucose in a period. And the method I'm interested in using is offline reinforcement learning. Before going to offline reinforcement learning, I want to share a bit about reinforcement learning. So the definition of reinforcement learning is by training an agent through a trial and error to perform optimal decision making. For example, I'm showing you an example of training a dog to perform sit when commanded. So in the first attempt, the dog may be walking or wandering around, but not sitting, which is the action that you take. And each action actually corresponds to different rewards. For example, if it's not sitting, we'll assign reward to be 0. And reinforcement and the corresponding return will be the sum of discounted reward in each step. So in the first step, we noticed that if it eventually sit in the time step 4, you will get a return of 0.9 to raised to the power 3 times meat. In the second attempt, the dog probably noticed that if the quicker it sits, it can get the meat sooner without starving. So eventually, the return will be increased into 0.9 squared times meat. And by training it for a third time, it realized it will get a higher return in final. So reinforcement learning for automating insulin infusion in real time is depicted as follows, is that we want to train an agent which take the past glucose as an environment feedback and then provide an action by giving insulin infusion dosage. However, the challenges to perform reinforcement learning in the setting of not only insulin infusion, but all biomedical research is that the safety. Because in our situation, we don't want the patient to suffer from hypoglycemia, which may lead to coma or hospitalization due to the training stage where trial and error happened. So the approach I'm interested in exploring is offline reinforcement learning, meaning that our trained agent does not interact with the patients, but rather interact with a buffer which collected the patient's past insulin glucose dynamics from wearable data. And here I'm presented you two different offline reinforcement learning and their performance for the corresponding patients that we see before. The two reinforcement learning algorithms are TD3 plus BC and also batch constrained Q-learning. And we can see that offline reinforcement learning could actually decrease the glucose variability compared to the offline data noted by the blue curve, and maintain them in the safer range depicted by this green shaded area. However, what happened in the vaccine is that I found algorithm performance depends a lot on the quality of offline data because every patient have different glucose trajectories. And I also found domain knowledge could help improve agent performance. For example, for those patients who have higher glucose levels over time, I try to expand the insulin search space rather than following the original paper. So in summary, I presented you how I infer patient-specific glucose insulin dynamics using systems biology, informed neural network, and wearable data. And also, I found offline reinforcement learning algorithm can be used to optimize insulin dosing when proper tuning happened in the vaccine. A broader impact of my work in this section is that I want to use offline data stored in the buffer obtained from different drugs to optimize personalized drug with better outcomes. For example, there are many insulins having different acting times, and we can take that into account. And more in the future for the methodology, there is also an opportunity of developing physics-informed neural network where the ordinary differential equation is replaced by partial differential equation and to address the variation of spatial and temporal patterns in drug delivery. So I'm hoping that I've shown you how the multi-scale modeling and machine learning can work together to provide a better diagnosis and prognosis of diseases. However, a very unsatisfying situation is that we found many clinical trials actually fail with a success rate from phase 1 to FDA approved to be only 9%. And the reason for the failure of many clinical trials is that they fail to account the personalized like interperson or intraperson differences. And my future work is trying to develop in silico model to improve the clinical trial design and offer personalized medicine. Specifically, by showing an example, I'm interested in exploring how in silico personalized medicine can help understanding respiratory diseases and also the corresponding drug designs by addressing the age and sex differences. There are both anatomical differences and hormonal differences in different sex and ages. For example, in aged patients, we found the lung tissue is much stiffer and the lung volume also decreased and muscles are weaker. And also in the sex differences, we found adult male lung is at least 10% smaller than the male man's given the same height. So to understand this transport advection diffusion reaction, I want to use multi-scale modeling combined with a physics-informed neural network to promote our understanding of age and sex factor in determining anatomical differences. Also, in a lower time and length scale, the hormonal differences also changes our drug responses in different age groups and different sexes. For example, in aged people, the thymus, which is where T cells get mature from, decrease, and also the size and the function both decrease, and leading to a less responsive in the adaptive immunity and leading to less vaccination response. Also, simultaneously, we know that sex hormone can also affect inflammation and pose different effect on different immune cells in the lung. So at this lower scale, I want to develop pharmacokinetic and pharmacodynamics models combined with the systems biology-informed neural network to explore opportunity to optimize the drug deliveries. And by taking this all together, I want to achieve the goal of biomarker discovery and estimating of the risk of disease or mortality, and hence design personalized drug depending on different dose, formula, and injection route. And also, by taking all this knowledge together, I want to optimize the general drug design with better efficacy and potency. Thank you. That's all my presentation today.
Thank you so much for your great presentation. Before opening the floor for a question, Nicholas is asking to talk about a specific, specifically on patient and specific information, how you provide it to the model. Can you go to that slide?
Patient-specific information. 26. Okay. This is 26, probably is before. Oh, here. Oh, yeah. So the patient-specific model will be used in the fine-tuning part, where we will, because it's like a two-step training. In the first step, we train a model on a bigger data set, meaning all the other patients that we had in hand with a similar diagnosis of, say, type 1 diabetic. And then the patient-specific data comes in the second step. When we fine-tune the model, we actually kind of retrain the model using a patient-specific data. Hope that answered your question.
Do we have any other questions for the speaker? I cannot see any other questions. George, do you have any comments?
I will send the Yixiang comments later.
Thank you very much.
So, do we have any other questions? No.
Just can I ask a
question? Can you introduce yourself first?
This is Arda from this is Arda from Spelman College Math Department. So regarding that inverse problem, actually, that biologically informed neural network problem. So how do you make sure that actually like the selection of parameters that is unique and it doesn't actually corrupt the model?
We did some like a post hoc. What do you mean? A parameter corrupt the model?
You have an OD system, some sort of OD system. And then you have parameters in the OD system. And using that, neural network design, and you estimate these parameters. And in many cases, OD models are over parameterized, right? Like you have, I don't know how many parameters are here. Like how do you make sure, like, because some combinations, biologically implausible combinations, can also lead to the same results, right? So how do you make sure those parameters are biologically actually plausible? Do you have some trained in the neural network design?
Yeah, actually, when the design of the systems biology, there is already a scaling layer. So we have constrained the parameter to be within the literature understandable range. That's one thing.
Okay, so initially
we consult. Yes, there is scaling layer. We confine the parameter to be within the range.
So it is like, in a conventional setting, you do parameter fitting, and in that case, you start with some initial conditions. So it's kind of like you start with some sort of plausible range.
Yes,
but it's
only exploring the plausible range.
Okay, so this is in the input. This is like as an input, is it around input layer, or you do this actually like after getting the outputs?
You mean the parameter of,
Yeah,
of
for the parameters.
the neural network or the ODE?
No, neural network parameters, because you are getting the parameters from actual like biologically informed neural network design, right?
The neural network parameter, you mean here?
Yeah, yeah. You estimate the ODE parameter from this neural network, right?
I see. The ODE parameter is has a different network.
Okay.
Yeah, and that we have the scaling layer.
It's an input layer or output layer? Like
So we start. It's output layer.
Okay, so at the end of the day, you just scale the parameters to a biologically plausible range, so that like
yes.
Okay.
Yes, because we want to, because when we evaluate how the model work, we need to solve some inverse problem. Sorry, some forward problem, right? So another parameter in that will be outputting the realistic parameters in this model to help solve the forward problem. Otherwise, we cannot be sure that that is correct.
Yeah. Okay. So, and also another question, maybe in the same line, does this, because looking at the network design, does this also come with some sort of sensitivity analysis on that? Because some parameters can be super sensitive to changes. How do you deal with it?
We perform a structural identification in the very beginning. I don't know if that counts as the sensitivity analysis that you implied.
At the beginning means like before the network design and everything?
Yes.
Or within
it's about the structure of the ODE.
Okay, so you perform that analysis first, then.
Yeah.
Okay. So do you estimate all the parameters, or you just estimate some of them actually in this setup?
I think I just estimate some of them, yeah.
Okay, so not because this here, in terms of hidden parameters, I think these are all of them, right?
Yeah, and also we had some ad hoc analysis. Some of the parameter actually is sensitive, and that actually correspond to our structural identification analysis, but some are not very sensitive in my point of view.
Okay.
Which, yeah.
So you just kind of
ad hoc.
You kind of keep those like sensitive parameters within the network, and then maybe set some values for the others. Okay. So thank you. That was
Ergil, I want to add something to this answer, because I've been working with this glucose insulin interaction model. We do the identifiability analysis before the neural network and training level to see, with this information in hand and with this data that we are using for the training the neural network, are all the parameters in the model identifiable or not? And then inside the neural network, we limit the space for searching the value of parameters to the to the plausible range that we can extract from the literature, to make sure that the value of parameters are like rational.
Yes.
And then we train the neural network to find the value of parameters.
Yeah, because I got the impression that, let's say in the ODE model, you have like, for example, 16 parameters. Do you have all the 16 parameters in the neural network or not? You have like some of them, right? Sensitive ones in the network.
I think this model has like 21 parameters, but I think with having fixed value of some of them, we are able to find the value of 16 or 17 of them, like to be identifiable.
Okay. That makes sense.
Yeah.
Okay. Thank you. Yeah.
Because I remember about this paper. Okay, do we have any other questions for the speaker? There's no more questions. Thank you for accepting our invitation. Thank you for your time.
Thank you so much for the
to give the
opportunity.
talk. Yeah. Now can you yeah, thank you so much. Vlad, can you hear me?
Yes, can you hear me?
Yeah. Can you share your screen to see if there is any problem? Yes. So now we move on to our second session. Okay, we will wait for. Yes, thank you so much. Our second speaker is Vlad Medvedev. He will be giving a talk on U-Net-PINN for 3D lithographic simulation and nano-optical design. Vlad is currently working towards the PhD degree in computational lithography and AI augmented simulation research group at Fraunhofer IISB, Erlangen, Germany. His research interests include the implementation of physics-informed deep learning solutions for the enhancement of lithographic output and the design of nano-optical devices. With that, you can start your presentation.
Yeah, thank you very nice for nice introduction. So the work I'm going to present today is results of cooperation of two research groups. It's AI augmented simulation and computational lithography groups of Fraunhofer Institute. So the resulting work will represent a developed deep learning approach for solving complex optical problems. Specifically, I will talk about physics-informed neural network with a unit architecture for lithographic simulations and nano-optical design. So some words about me. Originally, I am from Kazakhstan. I started my education in St. Petersburg, where I obtained the bachelor degree in electrical engineering and also basics of laser. Then I moved to Germany, where I studied the advanced optical technologies. I learned the computational optics and deep learning. And then finally, I could apply these knowledges in pursuing my PhD at Fraunhofer Institute about 1.5 years ago. The thesis topic was physics-informed neural network for lithographic simulation and also nano-optical design. Also, some words about our institute. So the Fraunhofer Society is quite large. Our institute located in Bavaria, in the Erlangen. So from one side, Fraunhofer specializes in the wide bandgap semiconductor. So for example, it includes development of technologies and semiconductor materials, the crystal growth. It also links the electrical energy and non-electric forms of energy for different simulations, and providing the necessary devices, interfaces, and power models. And another part of the institute is about efficient power electronics. So it includes the intelligent energy system, development of high power drives, battery system, energy system, storages, also developed advanced power electronic system for different electrical vehicles, motorsports, aerospace. And also we have a test center for electric cars. On this slide, you can see the full semiconductor manufacturing loop. And today, there are extensive use of computational lithography and computational imaging. So it is first of all done for improving of lithographic output, prediction of unwanted effects, and design and optimization of lithographic masks. Our department is called Modeling and Artificial Intelligence. So our research focus is in development of physical models and software, AI-assisted simulation, computational lithography and optics, multi-physics simulation, and also power electronics. So the agenda for today, I will start with introduction to idea of the physics-informed neural networks and our motivation, why we apply this in the field of UV lithography and also meta-surface simulation. Then I will show the network architecture, explain the training feature, the developed model. I will show the results of developed model in two use cases. It's lithographic mask and also the meta-surface. And then I will show the challenges we faced so far after 1.5 years of project development. And in the end, I will summarize our findings and explain how we can transfer our knowledge to other use cases. Okay, let's get started. I will start with the lithography use cases. So UV lithography is optical technology for semiconductor manufacturing of nanostructures. So the smallest feature we can place on a single chip. And UV stands for extreme ultraviolet light. So it uses very short wavelength. Such wavelength is absorbed by almost all materials. This is why UV lithography is purely reflective. However, this short wavelength allows the high resolution imaging and placing billions of transistors on a single chip. So UV light is generated in the plasma, then a collector brings it to some intermediate point, illuminator shapes the UV light to desired illumination scheme, and this scheme is incident to the UV mask, which is our object of interest. UV mask consists of absorbing layer, which contains the desired circuit scheme we are going to project on the wafer. Below absorbing layer, we have a multi-layer, which is basically provides whole reflection of light. So after all light is reflected, using the projection optics, we project it to the wafer. Interaction of UV light with such mask provides different complex optical effects, such as scattering, reflection, absorption, diffraction. And to accurately model this interaction, we need appropriate method for this. And this is done using the rigorous electromagnetic simulations, which has different challenges. First of all, the modeling has to be done with high accuracy. It should be done fast. And we are going to simulate large mask areas. So rigorous electromagnetic simulations assume solving scattering problem, which is done through numerical approximation of Maxwell equation. However, we do not solve this Maxwell equation in general. We are focused in the prediction of scattered electric field. We can omit several terms in the Maxwell equation, like electric and magnetic current densities. And we are going to do simulations in space. So from a given equation, we can substitute the magnetic part of the field and finally derive this set of equation, which corresponds to the vectorial representation of Helmholtz equation. And for a given mask, where we have this refractive index distribution, the solution of this equation will be the complex representation of electric field. So here you can see the amplitude profile of this field. So what's special about scattering in the EUV domain? First of all, we eliminate under the angle. So we use a monochromatic light. It's a plane wave, which propagates from top down and then scattered and diffracted. So you see here the standing waves, the shadowing, and also this interference patterns inside the multi-layer. Second, the structure of this mask, it contains sub-wavelength features like this thin multi-layers, and also the features larger than wavelength, like this mask features on the top. And third, it's used the complex material, so the real part attributed to the refraction and imaginary part to absorption of light. And here how this light looks from the top. And we are interested in this light reflected from the top because it propagates to the entrance pupil of the UV projection system. And finally, this light is used for image formation and lithographic imaging. For this reason, the accuracy of PIN model is evaluated mainly for this light above the mask. So this light above the mask is analyzed in the Fourier domain to derive some quantitative conclusions for the lithographic imaging. And we obtain the diffraction spectrum using the near to far field transformation or Fourier transform, and extract the far field metrics like this diffraction efficiency, for example, showing how amount of light redistributed between the discrete diffraction orders. And this diffracted light emerges at the exit pupil of the projection system and redirected to the wafer. So the total image, what you see here, showing the intensity distribution, is called aerial image. Is obtained by incoherent superposition of images obtained by all discrete source points. This is how the shape of our source. So for each of these points, we do the rigorous simulations and finally superpose the resulting diffracted light. And the goal of this work is to develop such a PIN model that would be parameterized towards different mask geometries, materials, and also the illumination, because we are going to illuminate from different directions to obtain the accurate image in the end. All right, yeah, the goal of the project initially was to develop a physics-assisted approach for the solving complex problem, and the idea was to develop a pin-based mask solver. However, we could also extend the applications of this solver to different subwavelength gratings and metastructures. The objective also includes the acceleration of existing numerical approaches, analysis of performance and scalability. At the moment, our PIN model is purely physics informed. We do not rely on any training data. However, as in future, we also can consider also coupling it with some numerical simulations for optimization of design or solving inverse problem like retrieval of the material properties or the source shape and so on. And I will start with the use case of EUV mask. So mask can have different features like 2D, like this contact hole, or 1D, like the line. Here you can see this cross-section through this mask. As I mentioned, we use oblique illumination, like plane wave, which contains the incident angle, phi, azimuthal angle, and also the wavelength. So the light propagates from top to down. However, we do not want it to be reflected back. This is why we simulate the infinite boundary conditions. So we truncate our domain, and this perfect match layer absorbed the ongoing radiation independent of the polarization or incident angle. On the left and right, we aim to simulate the periodic boundary conditions because a mask is repeated itself in the X and Y direction. So we do not simulate whole mask. We simulate the single period and assume that the same processes are happening in the neighboring domains. However, we cannot use traditional periodic boundary conditions where we simply copy left to the right because of oblique illumination. The electric field on the left side and the right side will be different. They will be out of phase by some amount. And to correct for this phase, we implement the Floquet block boundary conditions. And mask can also have different geometries, like the sidewall angle variations, the thickness of mask, the feature size of mask. Traditional way to solve this scattering problem is using the numerical solvers, which are iteratively solve the Maxwell equations by discretizing them in time, space, or frequency. However, if we're talking about large mask areas or like complex illumination, these methods can be computationally inefficient. As alternative, here's data-driven deep learning, which basically learns the input to output correlation. So for a given scattering problem, network would learn mapping for given mask to the output scattered electric field. However, this network require a huge amount of training data, and in case of UV lithography, amount of this data is limited because of difficulties in obtaining confidentiality requirements. And another limitation of data-driven deep learning is that they solve the scattering problem without Maxwell equation. So basically ignore information besides the Maxwell equation, which can describe the electromagnetic behavior and interaction of light with the nanostructures. And we propose an alternative to these two methods to address their limitation. It's a novel deep learning approach, physics-informed neural network. So what's the idea? It's deep learning approach that combines from one side the advantages of machine learning, like short inference time and generalization capabilities. And from other side, it's explicitly supervised by the governing physical laws. So PIN seamlessly integrate the information from the partial differential equation, in our case, it's Helmholtz equation, into the loss. And during training, we minimize its residual. So idea is very close to the traditional machine learning, where we aim to bring loss to zero after the training. And in this case, we also bring the residual, so the result of all summation and subtraction operation also bring to zero, and finally find unique solution. So we explore different architectures. We start with fully connected approach. However, we faced some limitations in the generalization capabilities. This is why we switched to U-Net, which contains a convolutional layer. So the input and output are pixel discrete. For the input is a array, is a mask, where the geometry and material information are encoded. And network is trained to predict the scattered electric field. Then we apply the boundary conditions to this field to find unique solution for a given mask instance and compute the derivatives on this using the finite difference approximation. We also decompose the electric field in 3 parts. So the scattered electric field we used for the lithographic imaging later. Incident field brings information about the illumination we use, and total field contains information about the near field. So the
Vlad, I have a question.
Yes.
Why did you do finite difference for the derivatives? Why didn't you do compute the automatic differentiation?
Our input, as I mentioned, our input and output are pixel discrete.
Oh, I see.
So
I see. The CNNs, yeah.
Yes, we have this uniform grid, and we
Sure, it's a CNN. Yeah.
Yes, discretize it on the E grid, and then on this E grid we compute derivative as a convolution with the 2 non-trainable kernels, one for electric field, magnetic field, and finally use the finite difference approximation scheme of 4th order.
Okay.
Okay, thank you for your question. Yes, so we compute the derivatives and insert all components into the PDE to compute the residual, which is also pixel discrete. As a traditional deep learning, we can compute the mean squared error, and finally from loss compute the gradients, and then the gradients are differentiated with respect to the network weights, and network is trained. And then iteratively we minimize the residual and finally find unique solution to the complex electric field for a given mask. Some more details on the architecture. So yeah, we start with encoder, which extracts the relevant feature from the mask and brings them to latent space, where we have the compressed representation of these features, and the decoder pass we do the upsampling. So the input is 3D mask, which has a voxel volume. It has 2 channels corresponding to the real and imaginary part of material, and the output are 6 output variables, 6 electric fields, basically corresponding to 3 pairs of real imaginary part of 3 field components, X, Y, and Z components of electric field. Yes, we can encode the geometry and material in this mask. However, as our initial goal to also parameterize towards the illumination parameters, which are scalar, we cannot encode them in this mask. This is why we additionally extended the architecture by adding the tuning network, which has fully connected architecture. So this tuning network dynamically tunes the second convolutional layer of the main U-Net. And finally, physics-based loss is informed about different wavelengths and also illumination angles. In this slide, you can see some ranges of parameters that we use for training. It's variations of geometry, material, illumination. For example, this model, you see the loss curve, was trained for different geometries, illumination at the same time. From first glance, we see good correlation between the validation loss and training loss. So we have no overfitting, and also we use the exponential learning rate decay. So we start with some spikes and finally bring to the come to some plateau. We use the MAPE as accuracy metric between difference between 2 images, and we track this online during the training. And what you see here is a good correlation between the loss and the MAPE, which means that physics that we embed in the model is correct, and also boundary conditions are correct. So we focused on this 3D model, and we trained it about a week because of expensive 3D convolutions. However, I would like to point your attention to the inference time, which takes milliseconds, and compared to the numerical solution used as a reference, it provides significant speed up. I will talk about the numerical solution later. And another feature that we implemented, first of all, it's adaptive loss weighting. Sometimes we use it when we have when the different loss components are in different range, like in this case, when we use the fixed loss weights. In case of adapted loss weights, finally we could bring them to the same range, so loss value. We also use the multi-GPU training. So basically it was done for speed up of training, also scaling to the large problems and models. We used the on-the-fly data generation, so we didn't pre-generate the dataset. We didn't waste time for loading the dataset, so we start training immediately. And at each training steps, these mask geometries and different illumination angles are generated randomly. So the longer we train, the better we explore the parameter range, and finally provide the better generalization capabilities. Because of sharp material transition, we used the smoothing of material basically to handle the numerical inaccuracies around these discontinuous interfaces. And yeah, as I mentioned, we use the learning rate scheduling. You can see this reducing of spikes during the training. All right, now I'd like to demonstrate the performance of trained model. First, for use case of the UV mask, we used the Dr. Rita software. It's software for photolithographic simulations developed by our institute. It contains different models. So for near field and far field evaluation, we used the waveguide mask solver. And then we used later this spectra coupled with the imaging models to extract some lithographic metrics. As evaluation metrics, we used the mean absolute percentage error and root mean squared error. And our modeling objective are evaluation of near field, so amplitude and phase profile, then doing near to far field transformation, and then using the spectra for lithographic imaging, where we can extract the target feature size, the contrast, also process windows, and also push-pin limits to predict the different optical effects. Some of them are really complex, so I will not show them today. Okay, let's start with the near field. As I mentioned, we are interested in the near field above the mask. So we illuminate mask from different directions. Our quasar source contains 4 poles, which correspond to different incident angle, small angle pole and large angle pole. And you see the difference in the far field. So as the pole is larger, incident angle has some more pronounced asymmetries in the near field. And these asymmetries are also transferred to the far field. So in this like diffraction efficiency shift in the diffraction orders. So for most of our simulations of top near field, the mean absolute percentage error didn't exceed 1%, which is high accuracy compared to another data-driven approach based on U-Net for near field prediction. And I would like to also point that our model didn't use any training data. Okay, then after we accurately extract the near field and the far field, we can use this diffraction spectra for lithographic imaging. So with each of this point, we compute the diffraction spectra and incoherently superpose them to obtain these images on the wafer. And then from the target feature, intensity target feature, we extract the cross-section. We see quite a good match between the pin prediction and the used waveguide numerical solver. And also the process windows has good overlap. It's one of accuracy metric for lithographic imaging. And also the predicted target feature size has an error of about 1%. The contrast has also good match. The value where we obtain the best contrast and the range where we obtain the appropriate required contrast. All right, then I would like to show how PIN predicts for different optical effects. I will start for effect of illumination. So most of reflection in the UV mask is provided by the multi-layer. Optical behavior of this multi-layer is can be described by Bragg's law, which is a function of both wavelength and illumination direction. So the efficiency of use of UV light can be related and is correlated with the reflectivity of this multi-layer. So the highest reflectivity, the better we use the light. However, this reflectivity has a very limited angular support. For example, for illumination angle larger than 10, we see significant drop of reflectivity. And this is why we model and train PIN for the range from 0 to 15, which is traditionally used in the UV lithography. And it also functions of the wavelength. Usually we use monochromatic light with 13.5, where we have the peak reflectivity. But for some cases, the polychromatic simulations, so from 13.2 to 13.8 are used. This is why we also train the wavelength range. Okay, we start with the effects of the different illumination direction. And this model was trained for different angles and also different geometries, specifically this size of the contact hole. So what you can see here, for angles below 10, we see increased asymmetries in the reflected UV light. So again, we analyze the light above the mask in this near field. And these asymmetries can contribute to the contrast loss if we illuminate from different directions. For angles larger than 10, we see significant drop of amplitude, which means that we are in this range. And PIN effectively captures this optical effect. And for most of experiments, we averaged the error. It was about 0.5% in predicted near field. And then we analyzed effects of illumination. So we did rigorous simulations for different wavelengths from 13 to 14 nanometers. Our mask is a 1D space feature. What you can see here, first of all, changes of in the near field. So the amplitude profile is changing, the interference patterns inside the multi-layer changing, the standing waves. And also we analyze this reflected light for different wavelengths. As you can see, for a wavelength of 13.5, where we have this peak reflectivity, we have the highest amplitude profile, which means that we reflected most of the light. And as far as we go to the left, to the right from this 13.5 reference value, the amplitude profile goes down. We all use the dipole illumination for the lithographic imaging. So for each of these points, we compute the reflected light and superposed this, and we also see good match in the predicted cross sections. So this is how the feature would look like on the wafer. As a accuracy metric, we use the center of gravity, which you can see here. Also quite a good match between the numerical solution and the PIN prediction. Then I would like to go to prediction of polarization effects. I start the explanation with this vectorial formulation of Helmholtz equation. For some problems, we can use scalar approaches. So basically decoupled modes, it's T-polarized light and TM-polarized light, which has a certain orientation perpendicular to the plane of incident. In case of TE, for example, where we set several field components to 0, and for example, these cross derivatives can be also neglected. This approach is valid for some use cases, for example, 2D problems where we have no material variation in X direction, or for use cases where we have small material contrast, like UV domain, where these cross derivatives in the full Helmholtz equation close to 0. However, the importance of vectorial formulation that I showed in the beginning becomes more important as far as we go to larger material contrast. For example, again, we look at the near field above the mask. However, we simulated trained PIN model for different materials. And what you see in this table, we investigated the accuracy of vectorial and scalar approaches for increased material contrast. For example, for TABN absorber, we go into palladium, where you have the largest material contrast, and you see that the accuracy of the scalar approaches deteriorates. Another motivation to implement vectorial formulation is when we go from 2D problem to 3D problem. In this case, we obtain the scattering at the absorber edges and the corners, and also partial conversion of polarization. In the EUV use case in the EV masks, this material contrast is very small, so polarization effects are very weak. This is why we will analyze these polarization effects for the metasurface use case, where we simulate the dielectric materials. And this will be next chapter. So about metasurfaces, I would like to point 3 main differences to previous use case. First of all, we illuminate the metasurface from the bottom and analyze the transmitted light, not the reflected light like in the case before. Second, the structures on the metasurface are sub-wavelength. All of them are like smaller than the used wavelength. And third difference, we have the larger material contrast. So before we used material close to surrounding air. In this case, we analyzed dielectrics from 1 to 2 in this case. However, they can be even larger. We trained a model for geometry variations and material variations. So basically, the height of these structures, they are called pillars or meta-atoms, and also width of this and the material of these meta-pillars. First observation from the training, the loss became less stable. The large loss values correspond to the samples with the large material contrast, corresponding to a refractive index of 2, and small corresponds to the low material contrast. Again, we achieved speed up compared to the numerical solver. So as far as going to larger metasurface area, this speed up introduced by PINN becomes more pronounced, like from going from 1 pillar to 3x3 pillar. And then coming back to the polarization effects. So what we see here, we used the TE polarized incident light, and we expected to get only the dominating field components, only the EX. However, because of these polarization effects, part of the TE mode was converted to the TM mode. So the part of the EX field components was leaked to the Y and Z components. Especially, they're not zero at the corners of the pillars and the edges. PINN demonstrate quite good accuracy in the RMSE metrics. We also analyze the phase, mainly of the dominating field component. The idea of metasurfaces is to achieve desired optical properties. In this case, it's phase delay of at least pi. So we should explore a parameter space and find difference between 2 configurations of pi. This can be used for the wavefront manipulation and also for the aberration. And in this case, we face our first challenge, which is large material contrast. So as I mentioned, we trained model for different materials and geometries to achieve this phase delay. We could achieve this. What you see here is far-field metrics for different physical parameters. It's diffraction efficiency showing amount of light in the 0 order and phase of 0 order. And this phase delay or phase difference of pi can be observed for the large material contrast. However, for the highest feature and this large material contrast, we obtain the largest error because of the strongest diffraction. The problem of largest error for the large material contrast is also mentioned in other research papers. So in this case, we explored the parameter by 900 simulations. In case of numerical solver, it took about 11 hours basically to simulate such images. In case of PINN, because of short inference time of milliseconds, it was about less than 1 minute. In this case, the challenge, these metasurfaces had refractive index of maximum 2, but some pillars may have even higher refractive index. In this case, we can expect even higher error for the large material contrast. At the moment, solutions, how we handle this, we use the material smoothing to basically handle these inaccuracies by convolving with Gaussian filter. And another solution can be Born approximation, which can address the large material contrast scattering, but we didn't test this yet. Another challenge we faced so far after 1.5 years, it's high GPU requirements. So at the moment, we use quite large model. So experimentally, we found that the minimum network depth should be at least 6 or even deeper. We use expensive 3D convolution at the moment, and another point we mentioned that accuracy matters. So for some use cases we use the accelerated GPU machine with mixed precision, and for some use cases it may fail. So we prefer to use the floating point 32 such machines. So when we try to use a resolution described 1 nanometer by 2 pixels, we mentioned that one sample takes about 172 gigabytes. So we cannot even put several samples in one batch. This is why we had to reduce resolution to obtain the results I showed before to 1 nanometer per 1 pixel. And another solution is training on multiple GPU, basically to combine their memories and to train larger models and larger batches. Third challenge faced is the limited resolution of 3D image. So as the case of UV mask, I showed these rectangular geometries. However, in reality, the geometries can be more advanced, like these curvilinear shapes, this X, Y top-down view from the mask. Or the metasurface can be not just rectangular, but can be circular or ellipsoidal. And you can imagine that describing such structures with pixels, especially voxels, will require large image sizes. And then convolution of these large image sizes will require high computational limits and high GPU requirements. And this can also be related to this multi-layer. So we also described our multi-layer with low resolution before. However, in reality, multi-layer can be with intermixing, so contains alternating thin layer. And to describe, for example, this thin layer with 2 decimal points would be challenging because we will need 47 voxels for a single layer, and the multi-layer has 40 of these layers. So again, the image size would increase and the computational limits would increase as well. These are our 3 main challenges we face so far. We are working to solve them. And finally, I can summarize. Yeah, at the beginning, the idea was to develop mask solver based on the PIN. However, we could broaden this application and finally developed some general PIN-based EMF solver, also for other problems like metasurface simulation. In both use cases of UV mask and metasurface, we achieved good prediction accuracy in the near field, far fields, and also in lithographic imaging. Network showed good generalization capabilities towards the physical parameters because we use this convolution operation, so the parameter sharing. And PIN doesn't not only predicts these metrics accurately, but also captures the important effects and really understands the given physics even without being trained on the data. And compared to other machine learning approach, we could achieve a bit more accurate results in the near field prediction, even without training on the data yet. And compared to the numerical solvers, we can provide the light scattering response for arbitrary mask geometries, materials, illuminations within milliseconds, and this provides significant speed up both in the metasurface use case and in the UV mask use case. At the moment, we did 3 publications. So we started with modeling of near-far field diffraction from very simple UV absorber, even without multi-layer. We used this fully connected approach at this moment and demonstrated our results on the conference on electromagnetism. Then we could consider more complex use case, so the real UV mask and the corresponding lithographic imaging. These results we demonstrated in the SP Advanced Lithography conference. And we also are going to show this mentioned polarization and oblique illumination effects next week in the France on another SPE conference. As an outlook, I would like to mention how PIN can be applied for other UV lithography and non-UV lithography applications. So as I mentioned, this can be desired source shape. So the more points we use, the more accurate our lithographic imaging is. In case of numerical solvers, each of these points will take one rigorous simulations. So you can imagine that total simulation time will explode for such setup. In case of PIN, it would take only several milliseconds. So this can provide significant speed up, and PIN can be applied in these partial coherent illuminations. PIN can be also applied for inverse design. At the moment we solved only forward problems, like optical proximity correction, where we basically add features to the mask to improve the lithographic output. It can be also source mask optimization and inverse lithographic technology. In case of nano-optical device, we are going to focus on the simulation of metasurfaces. So trained not only for geometries, but also for different illumination directions, consider non-rectangular shapes. And finally, PIN solver can provide really fast response in the diffraction and the far field metrics. That's all from my side. Thank you for your attention. I would be happy to answer your questions.
Thank you so much, Vlad, for your great talk. Now we open the floor for questions. Do we have any questions, George?
But I have a question. Vivek, you can go because I have to go somewhere. This is excellent results, but the way I understand the way you use pins is like for this parameterization, it's like an operator. This to me it looks like a U-Net neural operator with physics loss, because otherwise you wouldn't get the speed up, right? You train for all different parameters. Are you familiar with neural operators like
DeepONet? Yes, I mean, they take input the functions, but we take not the functions, but the real mask. I mean, real geometries, not the functions.
The geometry is a function. It doesn't have to be parametric geometry. So the shape can be also the parameters. If you have like a parameter range from there to there, they think of this as a linear function. It's really the same thing, because at the end you're not that's why your inference time is that you don't optimize again, right? For new and unseen data, you just infer directly.
Yes.
And therefore, yeah, that's like it's totally okay. It doesn't matter how we call it if the results are good. It is. I think maybe Vivek would agree that this is a U-Net neural operator.
Yeah, it is an operator.
The physics laws.
Yeah, the physics laws as of constraint. Yes, great job. Great results.
Thanks.
George, can I ask the question?
Yes, go on.
Okay. Hi, my name is Vivek and I'm a PhD student working with George. Firstly, great talk and great results. I have a couple of questions actually. So, firstly, can you go to the slide where you're showing the architecture? So where you are using finite difference for computing the physics laws and adding it as a soft constraint? Yes, I guess that's it. So regarding that, so what is the order of the finite difference you used for computing the derivatives?
Fourth
order. Have you tried the other orders and you saw you got improvement when you used higher orders? Or
we also tried second one, but fourth provides slightly better accuracy, but even slightly better, more computational efforts.
Okay, that's nice. So were you able to observe a decrease in the sensitivity to training data when you incorporated the physics laws? Like you said, like you incorporate physics laws to reduce the dependency on the huge volumes of the training data. So did you, by any chance, did you perform any experiment in which the dependency or the sensitivity to training data like drops faster? For
no. As I mentioned, we didn't train with any single reference data. I mean, it's purely physics based. We didn't yet observe this like drop yet.
Okay, that's fine. Okay, in the next slide, I thought you explained about the tuning.
Yes.
Where you fed the angles of the illumination as a parameter to the network, to a MLP. So can you explain what exactly you did from the output of the MLP to the U-Net?
Okay, so network takes, let's say, several, gets scalar parameters to the first layer, the nodes of the first layer. Then we have some weights of the trainable weights of this model. And finally, the last layer which has dimensions of n1, let's say, is reshaped to some kernel or window, which is not concatenated but convoluted with the tensor at this place. And this is why this tensor is informed about different eliminations. So in the original approach that we cite here, authors concatenated. So basically they used one channel less in this case, and they basically summed the channel from the tuning network to the end, and then going to encoder pass down and then decoder. We used not the concatenation, but the convolution with some trainable kernel from the tuning network.
Okay, so you used the convolution, you defined a convolutional kernel which is dependent on the lambda, psi, and theta, and then convolved it across the latent representations in the encoder.
Yes.
Great,
yes,
that's
exactly.
a nice idea. Yeah. Yeah, okay. That's great. Also, you have like 6 components you mentioned for the electric field. And regarding that, so did you say you trained them adaptively, each loss of each field adaptively? Can you explain more on that?
1 second.
Yep. I think you, yep.
Yes, here. What do you mean adaptively?
So did you say that the loss for the different fields, were they all summed together, or did you use different weighting?
Okay, we used, as I mentioned in this case, our loss is composed of 3 equations. Each equation contains 2 output variables, real and imaginary part.
Okay.
Then we basically concatenate the residual of each of these 3 losses and then backpropagate this loss.
Okay. Okay. Yep. Okay, that's fine. Can you go to, I think you mentioned something in one of your next slides. Can you go a few slides ahead? A few more. Maybe I misunderstood. So you just have the data loss and the physics loss, and you just trained. And yeah, okay.
We have no data loss.
Sorry?
We have no data loss.
You did not have data loss. Oh, okay. Okay, okay. So I misunderstood that. Sorry. Okay. And also, do you have a reason why the mixed precision failed?
Not really yet. Maybe because we use like 16 numbers after floating point instead of 32, and somehow during the training this error is accumulating because we rounded it. And I mean, this is the only explanation I have so far. But a lot of, I mean, users of these accelerated GPUs also relate to this.
So when you used float 32, it started working. Okay, great.
Yeah.
Thank you. That's all from me. Great talk again. And thank you for answering my questions. Thank you.
Thank you for your questions.
Do we have any other questions for the speaker? I think we don't have any other questions. So it's time to close the session. Thank you everybody for joining us today. Thank you Vlad and Yixiang for their talks. And I hope everybody has a great weekend ahead. Bye.
Bye-bye.